Okay, so this is the final video of Unit 2, Properties of Functions. We'll start with the diagrams, which you saw in an earlier video, hopefully, but we'll be more explicit about how they work. So um, call them functions slash relation diagrams. So the following is a way to illustrate a relation. It's helpful in lots of different ways. Um, Also, you can a function is a relation, so this works for functions too. Um, and note this is not the graph of function. This is a just a diagram. This is not the graph of a function. So we always have, the domain on the left and the codomain on the right. That way we know, normally we would draw the arrows from left to right to see, so that tells you which one's in the domain and codomain. But if we just agree that domain is always on the left, then we don't need arrows. We can just draw lines. So here is a possible relation. So we have, how did I do it? Like this. Like this. So there we go. Simple as that. If we want like it to be more concrete. All right, so we have like if these are actual elements, 1, 2, 3, 4, A, B, C, then the relation here would be, well, I see a line from 1 to A, I see a line from 2 to A, I see a line from 3 to B, and from 3 to C. So the relation consists of those 4 elements, those 4 ordered pairs. And just again, these lines denote relationships. Or I should say ordered pairs. So a pretty simple way to diagram things. It helps for illustrating certain points and certain concepts, especially the properties of functions we're going to cover next. So let's just jump right into that. So definitions, 3 properties of functions that we're going to cover right now. So for all of them, just let f be a function. And I'm going to use our function notation from the previous video. So we always know that A is the domain and B is the codomain. Oops. Okay. So F is injective, or some people say 1-to-1. If informally, or maybe like in plain English, if distinct inputs always lead to distinct outputs. If distinct inputs always lead to distinct outputs. So, in other words, for all A and B and A, if the inputs are distinct, right, because they're in A, so they're in the domain, so they're going to be inputs, then their outputs should be distinct. So an example of injective would be, as a diagram, I should say. So I'll do this for each definition because I think illustrating it is the most helpful. So injective means, anything that any two A, B, and C that are distinct, they'll go to distinct outputs. So, and actually, I think the illustration for not being injective is even more helpful. So not injective, what does that look like? So it means that this statement is false, that there exists some A and B that are distinct, but their outputs are the same. So again, that the logical negation of this quantifier or this quantified statement gives us that. So what it would be for to not be injective, something like this. If A and B, which are distinct, both go to the same output, like 1. So this is, why is this not injective? For the implication, the hypothesis, A not equals B, that's true. But for the conclusion, we do have A equals B. So f of A not equaling f of B is false. So this is the only way to make the if-then statement false, right, from unit 1, make the hypothesis true, A and B are distinct, but the conclusion false, that f of A actually does equal f of B. Okay. So there you go. So this is like what it would, this is the, I'll highlight that too. This is, the key reason it's not injective, because we have two different outputs, or sorry, two different inputs going to the same output. All right. Another important property of functions is something called surjectivity. F is surjective, also called onto. If, in plain English, everything in the codomain has something assigned to it. And in a more formal, logical way of saying it, or with some of our notation, right, for all y in B, right, that's quote unquote everything in the codomain. For every element in the codomain, there exists an element in the domain that is assigned to that element. So and we kind of actually see two quantifiers, right, in this statement. So for all elements in the codomain, for all y in the codomain, there exists an A in the domain such that f takes A to y. That's what it means to be surjective. And here is some examples. Well, one example of surjective and one example of not surjective. So, surjective would be something like this: A, B, C, D, 1, 2, 3. So something like this. So how do you kind of check surjectivity? Well, you look at the codomain and make sure there's always some line pointing to it, right? So you say, okay, something goes to 1. Yes, A does, so does B. Um, something goes to 2. Yep. And then something goes to 3. So not that you would realistically be checking surjectivity by checking every single output. For example, what if there are infinitely many outputs? But it's just, I'm just trying to illustrate the definition. And so not surjective would be, well, that doesn't happen. So let's illustrate it. So we'll do the same. Actually, I'll do different domain and codomain. Do the same one. So we could have like A and B go to 1, and then C and D go to 2. And okay, something goes to 1, yes, something goes to 2, yes, but nothing goes to 3. Therefore, it's not surjective, right? And uh, let's go to the the logical statement and like negate it and just practice that unit 1 stuff. Um, so the negation of surjective, well, you have, maybe I'll put it a little bit more. So what does surjective mean? Well, what is it in logical symbols? For all y in B, there exists an A in A such that f of A equals y. I'm going to actually move this down here. So this is not the negation. This is surjective. So this is this statement, but just purely in logical symbols. So the negation of it is equivalent to, well, remember we have De Morgan's laws for predicates. You can pull the predicate through and then flip the quantifier, right? So if you say for all something, blah, 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 well, the negation would be there exists something where it's not true. So it would be there exists a y in B such that this is not true. Okay, this is just De Morgan's law. And then, okay, well, let's do that again because, right, we have another negation that we can kind of pull through the quantifier. And again, for there not to exist something, that means that for all of them, it's false. So how do we write that? So then this part is still the same. There exists a y and b such that, but now it's for all a and a, this is false. F of a equals y is false. Okay, this is again just De Morgan's law. The other one. Let me scooch this up a little bit. And then, right, what's the negation of equaling? Not equaling. So the last step to simplify this would be there exists a y in B such that for all a and a, f of a is not equal to y. And let's just check that that statement logically matches up with our illustration, right? So for something not to be surjective, there has to exist a y. Okay, that's 3. A y and b, I'm sorry. That's 3. Such that for all of these elements in the domain, um, they are not going to equal 3. And that's true. F of A equals 1, F of B equals 1, F of C equals 2, F of D equals 2. None of them equal 3. So therefore, yeah, it checks out. So I just wanted to show you the connections between Unit 1 and Unit 2, right? And really Unit 1 and like all of mathematics and computer science, because logic is at the foundation of all of that. Just want to see so you can see it in action. All right, last property of functions. And now that we have the first two, this one's kind of the easiest to describe. Um, so the function is bijective, also called, um, well, that doesn't really have a good alternative name, but yeah, if it is both injective and surjective. You also sometimes call bijective functions one-to-one correspondence. So to be both bijective and surjective, something like this, well, okay, well, there's different bijective functions you could make here, but here's one. Is it injective? Distinct outputs should, or sorry, distinct inputs should always lead to distinct outputs. Yep. There's no like, this is not happening. So we don't see any two inputs going to the same output. So it's injective. And it's surjective because we see everything in the codomain is getting hit by something. Right? So we're good there. Okay. Now I want to connect these properties of functions to the last video you watched, the YouTube video by Up and Adam on the pigeonhole principle. So we can actually see the pigeonhole principle in the context of functions. Of course, because of how the videos are named and the way I ordered them in the module, hopefully you watched that video before this one, 2D before 2E, this one. But just recall the pigeonhole principle. So if you have more pigeons than holes, there will be a hole with multiple pigeons. And in the video, you saw the, like a grid of with 4 boxes, the holes, and she was trying to put 5 pigeons in there, and of course, 2 had to share one of them. Um, I don't I don't know where I heard this, but I don't think that is how, like, why it's called the pigeonhole principle, even though every YouTube video you'll see or every explainer will be like, oh yeah, it's about stuffing pigeons into holes. That seems kind of violent. I'm pretty sure it came from just letters like in the mail going into people's mailboxes, and they're called pigeonholes because they used to be taken by carrier pigeon. So I think it's much less violent than what every other YouTube video suggests out there. But it doesn't matter. Getting stuffing pigeons into holes is very, it sticks with you. So let's diagram basically what we saw in the video in terms of functions. So if this is the pigeons, wow, that's terrible handwriting. This is the pigeons, and this is the holes, right? In the video, there were 5 pigeons. and there were four holes. And okay, so you're like, well, let's try and give them as much room as possible. So we'll just, do that, do that, do that. But then once you get to the fifth pigeon, there's nowhere to put them. There's no empty hole to put them in, so it has to share a hole with someone else. And so you have that. And that situation should exactly remind you of one of the three properties, or, more specifically, not having one of the three properties. Um, so remember, we have distinct outputs leading to the same input. So that means not injective. And so another way to state the pigeonhole principle is just in terms of functions. So reframing of pigeonhole principle. So if A and B are finite sets, such that A has more elements than B. Whoa. So if A and B are finite sets such that A has more elements than B, there cannot be an injective function from A to B. So that's another way of stating the pigeonhole principle without harming any pigeons. But really just in order to see it in the context of functions and their properties. And this is a very useful tool in a lot of problem solving applications. I mean, I've even used it in my own research. And as you saw in the video, right, you can prove that there can be no like completely lossless compression algorithm that works for any kind of data. Um, and the list goes on of applications of the pigeonhole principle. One other thing I want to say too is these do have to be finite. So I say they're finite and A has more elements than B. That only works when they're both finite. Um, the last video, the video 2D, the up and atom video, I cut it off at like 8.5 minutes. If you go find it and watch the rest of it, um, she does a good job of explaining what happens when sets are infinite and how the pigeonhole principle might not apply. So just note that both sets have to be finite for this to even make sense. Okay. Lastly, I'll give you a series of questions. So um, I'm going to give you a series of diagrams. I'm going to draw a diagram and then ask you a question, and you're going to basically check all the boxes that apply, whether it's injective, surjective, or not even a function. Okay, so let's get that going. I'll say properties, property, or IES, could be multiple properties. So I'm going to draw a relation, and then the question will pop up. You'll say, and it'll be injective, surjective, or not even a function. Um, and check all that apply. Okay, so the first one, and I'm not even going to bother naming the elements, just use dots. All right, that's it. Nice work.